Okay, now let us go to the next property, which is the time shifting. Time shifting property. Now this property says that if the periodic signal x of n is shifted to x of n minus n naught, that means the signal is delayed by a factor of n naught, or it may be advanced by a factor of n naught as well, then the corresponding Fourier series coefficient will be changed by c of k e to the power jk omega naught n naught, and for this case the coefficient will be c of k e to the power jk omega naught n naught, and a negative sign for the advance of the signal. Now let us recollect what is a signal shifting. If this is t and x of t, I am showing it for the continuous time signal, but the discrete time signal, the output is quite similar. If this is the signal, this is 0, 1, 1. So if the signal is advanced to, delayed by 1 unit, the signal becomes like this. This is 1, 1 to 2, and this is 0. That means the amplitude does not change. What changes is the position of the signal in the time axis. Similarly, if the signal is delayed, advanced by a factor of 1, this becomes like this. This is minus 1, minus 2, amplitude remains the same, 0, t. So now if a signal is shifted, here we have shifted it by 1. So now if the signal is shifted by, say, n naught, the corresponding Fourier series coefficient c of k will itself remain the same. Only another term will come, which is e to the power jk omega naught n naught, where n naught here is the units shifted. Hope that's clear. Now let us consider the frequency shifting property. Now, the frequency shifting property is complementary of the time shifting property. That means they are vice versa. What we are doing now is that we shall be shifting the value of c of k in the frequency domain and then see the consequence that it makes in the time domain. Now, if c of k is shifted, that is delayed by a value of m, in the frequency domain, where say c of k is this function. Now if it is delayed by an amount of m, this part being m, the corresponding change in the time domain will be something like this. C of k minus m will give x of n e to the power j omega naught n times m. And consequently, if c is advanced by m factor, the time domain equivalent will be x of n e to the power minus j omega naught n m. So, in doing so, what are the utility of this property? As you see, using this property, the calculation becomes quite easier when solving any mathematical or analytical problems. As for example, if you are given a function of c of k, I mean x of n, which yields the Fourier series coefficient of c of k, and you are asked to do it for x of n minus m, you don't need to calculate this using the synthesis or the analysis equation. Rather, you can easily write from the time shift property, this will be c of k e to the power jk omega naught n naught. So, these properties has made the life easier for calculating mathematical problems. Now, let's go to the fourth property, which is the conjugation property. Under this property, if x of n gives the Fourier series coefficient c of k, then x star n, where star means the conjugate of n, so x conjugate n will give the Fourier series coefficient equals to c conjugate of minus k. Now the fifth property is the time reversal property. Which says that if the signal x of n gives us the Fourier series coefficient of c of k, then if the signal is reversed in time and becomes x of minus n, the Fourier series coefficient will be c of minus k. Now, what is a time reversal? If this is the signal, say x of t, then x of minus t x of minus t will be, say this is 1, this function. Now, if you look closely, it is quite simple to understand that if this signal has a Fourier series coefficient of c of k, this will also have the Fourier series coefficient of c of minus k, because the signal in itself haven't changed, only its value in the time axis has changed. So this is the time reversal property. Now let us go to the sixth property, which is the time scaling property. The time scaling property. Now this property says that if a signal x of n is scaled in the time axis, suppose is divided by a scaling factor of m, then its consequent Fourier series coefficient will be 1 over m, this is small m, 1 over small m times c of k. Once again, the Fourier series coefficient remains same, only what we need to do is multiply the Fourier series coefficient by the scaling factor. Before that, what is time scaling? Say, this is the signal x of t, this is 2, this is also 2, t. Now if the signal is scaled to x of twice t, the signal will become compressed. Compressed in the sense amplitude will remain the same, but the signal will start from 1 rather than 2. So the signal becomes compressed along this direction. And similar is the case for, say, x of t over 2, where the signal becomes expanded. Instead of 2, the signal will end at 4. So this is nothing but the contraction and rarefaction of the signal, which is the time scaling. Now, another important property, which is the multiplication property. And this property is quite important in frequency analysis. It says that if two signals x of n and y of n are multiplied, then their coefficients will be, the coefficients will be equal to the conjugate of one another. Say if k of n equals x of n times y of n, then if k of n's Fourier series coefficient is, say, w of k, then w of k will be equal to c of k conjugate of d of k. And of course conjugation means taking a running sum where m goes from 0 to n minus 1, c of m and d of k minus m. Now in the convolution, this is the convolution, what I meant to say, not the conjugation. In the convolution property, it says that if the signals x of n and y of n are convoluted to one another, then in the frequency domain, their Fourier series coefficient will be multiplied to one another. Similarly, if this is k of n, then w of k will be equal such that the coefficient of x of n and d of k, when multiplied, will result in w of k. So these two properties are complementary, or vice versa, you may say. The ninth property in our case is the property of symmetry of a real signal. Now if x of n is the real signal, and what do I mean by real signal? Say x of n can be a signal which is equal to, say for instance, cos of thrice pi n. This is a real signal. And what if the signal is imaginary? X of n is said to be an imaginary signal if x of n is written as e to the power j of twice pi say n. So this signal does not have an imaginary part. So this is a real signal, and this signal obviously has an imaginary part which can be written using the Euler's relation. This can be written as cosine of twice pi n plus j sine of twice pi n. So since this signal is having an imaginary part, So this signal is obviously not real. So in our case, if x of n is real, that means devoid of any imaginary part, then we can write C of k is equal to C of minus k conjugate. Hope that is clear. So for a real signal, if you can find out the positive values of C of k, you don't need to find out most of the negative values. What I mean to say is that if you have found out C of 1, C of 2, C of 3, you can simply find out C of minus 1 to be equal to the conjugate of C of 1, C of 2, which is equal to the conjugate of C of minus 2, and C of 3, which is the conjugate of equal to C of, minus 2 equal to the conjugate of C of 2, and consequently the C of minus 3 equal to the conjugate of C of 3. So this makes life much more easier in mathematical calculation. Moving on to the 10th property. The 10th property being the property of real and even signal. Property of real and even signal. Okay, let us go back to the first lecture. I have defined what is a real signal in this lecture, and what about an even signal? As I have said, an even signal is a signal, say for instance, this signal. The even signal states that when a signal is mirrored about the y-axis, will give a similar result. That means the same result is found when this part of the signal is mirrored along the y-axis in this direction, which is similar to the right hand side. So this signal is an even signal. And what about an odd signal? The odd signal says that if the signal, say something like this, is mirrored about the y-axis, it will also give the same value but in the negative direction. So instead of this signal going like this, it will start from here. This signal starts as the negative in the negative y-axis, negative x-axis. Now what about if this signal was an even signal? Say for instance, if this signal is made to be even, it will look like this. This part will remain the same. And I have said, in case of even signal, if we mirror the signal, it will give the same value. That means, along with the sign of the values, that means that if they start from the positive direction, this signal will also start from the positive direction, and go on, so on and so forth. But if it is a negative signal, this signal will look like this. Now, we come back to the property where x of n, when is real and even in nature, then the Fourier series coefficient C of k will also be real and even. This is the property of real and even signal. So upon looking upon a signal, we can easily tell the nature of the Fourier series coefficient of the signal. So for this signal, if we plot the Fourier series coefficient, it will also be an real and even signal. Now let us go to the next property. The last property, which is property of real and odd signal. Now if your signal x of n, as I have shown before, say x of n goes something like this, is real but odd in nature, then what happens? So x of n is real plus odd. What happens to C of k? C of k then becomes imaginary and also odd. It remains odd, but it becomes imaginary. These matters will become clear once we go into the mathematical problems, where we will learn to draw the frequency spectrum, the phase spectrum, and the magnitude spectrum of signals. Okay, now with that we will conclude the property of Fourier series. So there are 11 properties, which is very useful for the mathematical calculations of Fourier series coefficients. We shall now move on to the next part of the video, to the next topic, which is the power density spectrum for discrete time periodic signals.